We left on Friday talking about adaptations in blood volume to aerobic training. Okay? You run, you bike, you elliptical, whatever it is, and the next day your blood volume has gone up. Okay? More blood volume, more preload. Right? Greater cardiac output. All of this stuff helps. Makes VO2 max go up. Okay? More blood volume, more stroke volume, higher VO2 max. As I said, this is what I call a persistent acute effect. Run today, you get a couple of days of expanded plasma volume. As long as you run again before, right, out of that 48 to 72 hour window, you get it again. And again, and again, and again. Which then leads to, over a month, or 2 months, or 3 months, or 6 months, more blood volume. Okay? It starts off with plasma, and then as the plasma volume goes up, we will also begin to stimulate red blood cell synthesis. And there'll be a little bit of a couple of week delay, but plasma goes up and then red cells go up to catch up. Okay? So initially, you have a certain amount of red cells in your 5 liters of blood volume. As plasma volume goes up, your red cell percentage, so your hematocrit percentage, actually falls ever so slightly. And then red cell content will catch up, so you end up back at the same sort of hematocrit percentage place. Okay? And so it looks, if I can make it work, it looks like what's on the right here. Okay? This is days of physical activity. The percent, that's delta, so the percent change, and you can see the dark circles are overall blood volume. The white circles are plasma volume, and then the white squares are red cells that are going to move out as we kind of move along. Okay? So in this particular study, you will note that initial kind of big spike in plasma volume. Okay? And then you will see then that kind of lag and delay in red cell volume that catches back up. And so then the plasma volume kind of comes back down a little bit, and we end up in this group at about a 10% increase in blood volume, where hematocrit percentage normalizes back out to stay the same. Okay, that's what happens in most people. In longer term training, you may be able to see up to a 20 to 25% total increase, whereas in that study it was just about 10. Okay, so if you have 5 liters of blood, you can add a liter of blood with long-term training. Okay, with long-term training. And you may ask, this is great, Dr. Black, but why do we give a shit? Okay, look at the graph on the left. Okay, this is blood volume in milliliters of blood per kilogram of body weight. So it's blood volume per body weight, graphed against VO2 max. And what you will notice that as blood volume per body weight goes up, so does your VO2 max. Okay? Very, very, very tight correlation between increasing blood volume and increasing VO2 max. If you have a larger blood volume per body size, you're going to be more fit. And a lot of that is, it's kind of the chicken or the egg, right? That as you become more fit, you drive the blood volume adaptation. But as I told you guys last week, if I give you 2 pints of red cells today, I make your blood volume go up right now. Okay, your VO2 max immediately goes up. Part of that's from an increased stroke volume. Okay, the other part is from having more, just physically more red blood cells. You can carry more oxygen, so it makes extraction better. So it affects stroke volume and AVO2 difference. Very, very, very powerful adaptation. We probably don't have the scope and the time in class to talk about this, but if you want your red cell count to go up as a percentage of your total blood volume, that's when you need to go to altitude. Okay? Go live in Denver. right, for several months, and your hematocrit percentage goes up. Okay, go to Denver and train while you're in Denver. Okay, and you're going to get an expansion of total volume and an expansion of red cells as a percentage. Okay, altitude does some weird things. Okay, but that's the general thing. Okay.
Is there a certain amount of time you need to train in altitude, or is it?
So I'll clarify. Technically, you want to live at altitude, but not train at altitude. You want to train down the mountain somewhere. Okay? Because when you live at altitude, there's less air, less oxygen, that stimulates erythropoietin, that stimulates red cells. But by being at altitude, you limit the ability to saturate the red cells when you're exercising, so it actually reduces your VO2 max. So you can't train quite as hard. So what you want is, you want to sleep in the O2 deprivation tent while you're at sea level, so you can drive red cells, but be able to train where there's plenty of oxygen. But to your question, I mean, you need to live, you want to live, I don't know, I mean, you'll get adaptation within a couple of weeks. It takes, I don't know, 2 to 4 weeks to get new red cells, depending upon who you are and how it goes. So you need to live there for several months, if possible. Okay.
So I actually grew up in Colorado, and then obviously I moved here.
Yeah.
So let's say like I didn't exercise at all, would I lose just from moving from Colorado to here? Would I lose all of these effects?
Yes. You have about a 90 to 120 day sort of turnover in red blood cells. And so as you go from there down, then you're going to lose some of that stimulus. And so it may take several months, but your hematocrit percentage will fall back down. The interesting thing is that as soon as you come back down to sea level, though, you get an expansion of plasma volume. One of the things that happens when you acutely go to altitude is you pee more. You purposely dehydrate yourself when you go to altitude to raise your hematocrit percentage. So your blood volume falls, but your hematocrit percentage goes up within just a couple of days of going to altitude. And so then it takes a little bit of time for your red cell count to come back up and you get your plasma volume back up a little bit. So there's these weird competing adaptations that go on. Okay, but watch yourself. Anytime you go from here, like you go up to the mountains and you walk around, you're like, it's real. It's a real sort of effect. There's just less air. So got Miles, and then somebody was over here. No, okay, Miles.
You said training at altitude actually decreases your VO2 max?
No. If I said that, I misspoke. To maximize training adaptations, you want to train at sea level because you can train harder. You can do more work at sea level because as you go to altitude, just because there's less air, then your VO2 max declines. Right? No matter how trained you are, no matter what the adaptations you've had to compensate are, your VO2 max is always lower at altitude than it is at sea level because there's just less oxygen in the air.
Is training at altitude that makes you more in shape whenever you come back down to sea level?
The adaptations that come from being at altitude, having more red cells, absolutely transfers and would improve your VO2 max at sea level. But you get some of that, but you just can't train as hard, right? You just can't run as far, as fast, or bike or whatever at altitude as you can at sea level. And so if you're an elite athlete, you need to be able to push really, really hard, right? To maximize that last little bit of adaptation. And so in that way, it's not going to work. In most of us, yeah, go to altitude, train at altitude. Who cares if your VO2 max is down a little bit? We're not in that good a shape anyway. We'll get plenty of adaptation. Okay. Good question. Altitude's wild. They've done a whole bunch of studies. They'll go to base camp at Mount Everest and like carry a metabolic car to an exercise bike like up to base camp at Mount Everest and just test people as they come through, test them while they're at base camp for several weeks to acclimatize and watch how blood volume shifts and VO2 max shifts while they're at base camp acclimatizing. Ty, Google how high is base camp? I feel like base camp if you want to try to climb Everest, is like higher than any mountain in the sort of in North America anywhere, right?
Base camp is at an altitude of 17,598 feet.
Base camp is 2,000 feet, right? The top of Pikes Peak is like 12 or something, I think, 13. I'm trying to remember.
14,000.
13?
14.
14, okay. We rode the train up last summer with Ellis to Pikes Peak on all of that. I mean, it's tough to walk around this where you're way out of shape like that. Okay, so base camp is way above that. And you gotta go and you gotta sit there, right, for weeks to try to stimulate some red cell content and to get a class. Okay, really cool stuff. All right, so let's talk about ABO2 difference in general. Not the underlying things that are going on, not the underlying things with red cells and stuff. If I just look at the ABO2 difference of you before you train and after you train, okay? At rest, there's basically no difference as long as your muscle mass and your body size hasn't changed. Okay? You need X amount of oxygen to sit there and exist. We're at sea level. Red cells are basically 100% saturated. It's not going to change. It's not going to change very much during submaximal exercise. Where we see differences in ABO2 difference is at the top end. At your VO2 max, as max goes up, ABO2 difference can go up. And so what's happening for the most part is it allows you to do higher levels of work and therefore extract. Because ABO2 difference is determined by capillaries, it's determined by mitochondria, it's determined by O2 saturation and total red cell count. Okay? And so during submaximal stuff, that doesn't matter because you've got plenty. But at max, as those things increase, your max ABO2 difference is going to go up. Okay? So, kind of like with ventilation, that's what's going on there. If you're a normotensive person, training has no effect on your blood pressure. Okay? If you are 120/80, which no one is, and they'll decide that's pre-hypertensive at some point, right? I got my physical last week, and I was 120/72, which I promise you the nurse did not take it correctly on all of that. I've had it done enough. I've done blood pressure enough. There's no way. All they're doing is just making sure that I'm not like 160 over something, right? They went way too freaking fast for those kinds of things. But I'm 120/72, okay? Train all I want, it's not changing. I'm normotensive. It's not going to change. No matter what kind of remodeling I get in my arteries and arterioles, no matter what happens to total peripheral resistance or resting epinephrine or epinephrine levels, it's not going to change. Okay? However, if you're a person that is hypertensive, you're 160/90 or worse, it's going to go down. 8 to 10, maybe up to 15 millimeters of mercury. Most people are in the 8 to 10 range. Okay? If you're hypertensive, we can get it to go down. How? Why? No idea. No clue. They've observed it for 50 years. We still don't know why. We still don't know. Okay? Is it some combination of sympathetic outflow at rest? Is it some combination of remodeling? Probably, right? But we don't fully understand. Okay? If you are a person that is hypertensive, the first thing the doctor's going to have you do is try to increase physical activity and stop eating salty foods. I'd be so screwed. So screwed. Right. Chips, garlic bread, oh, gets me where I live. Okay? But that's what's going to happen. You're going to get a little bit of a change, but only if you're hypertensive. Okay. I said you might get some remodeling in arteries. There are big changes that happen in your arteries with aerobic training, okay, or physical activity in general. So we're going to talk about two processes. The first one is called arteriosclerosis. Okay, arteriogenesis. This is take the arteries that you have and make them bigger. Okay, and make them bigger. So what you can see here, this is called vascular remodeling. Okay, here on the left panel, what you see in these bars is the change in femoral artery diameter. How big is the femoral artery? How big is that sort of large pipe that's going to bring blood to the lower body? Okay, and so what you can see here where it says baseline, that's basically an untrained sedentary adult. Okay, and you can see then 8 weeks of training, 12 weeks of training, endurance athletes on the right, they have larger femoral arteries. As we go to the left, these are data from a bunch of studies. If you have a cast on your leg for 1 week, you're losing like 5% of femoral artery diameter by being in a cast for a week. Okay? Here, ULLS is unilateral lower limb suspension. This is the thing that I told you guys about before, I think, where we model space flight. Giant platform on one shoe, one leg just swings around for a month. You bear no weight on it in that leg, right? Again, about 10%, 4 weeks of bed rest. Okay, again, about 10%, 7 weeks, 9 weeks. NASA does these crazy studies. Well, they'll put people on bed rest as they study the effects of space flight. They put you on bed rest and you're in like head down tilt, right? A little better for the brain, be a little bit of head down tilt on all of this for up to like 12 or 16 weeks. Because they're trying to model people going to the International Space Station. And so if you have an idea for a study, you can submit your protocol to NASA. And if they like it, they'll just do it for you while they've got these people on bed rest. Okay. But so they've done these bed rests. Here's this spinal cord injury, 3 weeks after a spinal cord injury. Okay, 25% drop. Chronic spinal cord injury down about 30%. So as part of my master's and PhD, we did a lot of work with spinal cord injured individuals. We made these measures on those folks. Tiny femoral arteries, tiny. Then when you bring people in and you test them and they're endurance athletes, and they have these just giant, like Super Mario Bros., kind of like giant pipes. All of these things, okay? Here is, right, the change in femoral wall thickness. So it's not just the diameter, but it's the thickness of the wall, okay? A thicker vessel wall is indicative of poor outcomes. It means when you get changes in blood pressure, it is more difficult for that pressure to get deflected through the vessel, and it will raise the pressure, increasing the chances of blood clots and atherosclerosis and a whole bunch of things. And you will note, right, it's basically the opposite. As we train, the artery gets bigger and the wall gets thinner or stays thin, which means it's very what we call compliant. It's very sort of like a rubber band. It will stretch and come back, stretch and come back. That's what you want your arteries to be. Okay? That's the femoral artery. Hard to get a blood clot in the femoral artery. Where you really want this is in your coronary arteries. Okay? You want them to be larger diameter and very compliant. So stretch and come back and stretch and come back. So you do not get blood clots there and end up having a heart attack or something. Okay? So the question is, why does this happen? From the last test that some of you struggled with, during exercise, what happens to arteries, and especially arterioles, to help me get more blood to a tissue during exercise? If I start doing curls, right, or it's Monday, we'll bench press. I'm bench pressing on Monday. What is happening to my brachial artery diameter as I'm doing this? It's dilated, it's getting bigger. Okay? I'm pushing more blood through. Right? I'm changing epinephrine or norepinephrine levels. I'm getting that local auto-regulation control to make them dilate. I'm stretching them. Okay? That seems to stimulate remodeling to make the diameter bigger and to make the wall thinner. Okay? It's the simple act of raising the flow through there and making it dilate. Seems to do those things. Okay? So that's why when you exercise, the muscles or the vessels that lead to the muscles you're exercising tend to be the ones that remodel. Okay? Now, here's some of that actual pathway. You do not have to know this. Okay? But a lot of it is driven by shear stress from increased blood velocity and that cyclic stretch where you're going to get a blood pressure deflection going through there. Every time, right, you get a ventricular contraction, pressure wave kind of pulls and pushes it out. Okay? It's driven by something called eNOS, which stands for endothelial derived nitric oxide synthase, which you don't have to know. Okay? But if you go to Dr. Kellerman's lab, they study this. Okay? You go to Dr. Paddock's lab, he's up and running in just a little bit. They study these things. The other thing is there's a signaling molecule called VEGF. I just like the name. It stands for vascular endothelial growth factor. Okay? VEGF. If I inject you with VEGF, it will help get remodeling of these things. Exercise stimulates all of this. Being sedentary inhibits a lot of this. And that's why exercising is really, really, really good for your blood vessels. Okay. So that's arteriogenesis. The other adaptation that we get, we've already talked about a little bit, but it's called angiogenesis. Okay, angiogenesis. Angiogenesis is the process of getting more blood vessels, more, especially capillaries, and branching off of those terminal arterioles. So bigger feed arteries, more small capillaries and things to get blood flow directly into those muscles that we need. Okay, so we increase capillary density, we get more capillaries per muscle fiber. It really seems to happen in 2A type fibers. Okay, and what this does is it's stimulated by the same things: nitric oxide, VEGF, changes in pressure. Okay, the same kind of things that make the femoral or the brachial arteries get bigger also gets us more capillaries down at the muscle level. And as we talked about last week, this limits fatigue. It improves AVO2 difference because it shortens the distance oxygen has to move to get into a fiber. Okay. It slows blood flow, so there's more time for O2 and CO2 to diffuse, for carbs and fat to go in, and it increases our ability to remove lactic acid. Okay. So arteriogenesis, bigger arteries, bigger diameter, that's good. Okay. Angiogenesis, more capillaries. And it's to an extent more of the kind of last order arterioles. Okay. We kind of get a double whammy on all of them. It's easier in the conduit arteries to get it to a place, and then we've got more of those small ones to slow it down and put it in close contact with those muscles. Here's a graph, and I got this from a review article that was published in 2011, but these data are from the 1970s, okay? And what you can see is on the x-axis is VO2 max. On the y-axis is capillary density, the number of capillaries per muscle fiber, or to the size of a muscle fiber, right? And it looks just in some ways like the blood volume to VO2 max thing, that as capillary density increases, that correlates very strongly with high VO2s. Okay, with high VO2s. So having lots of capillaries is very powerful for allowing more diffusion of oxygen into the muscles. In most instances, and I'll show you guys this in a minute, right? We double mitochondria. Yet, none of you usually are able to double your VO2 max. Okay? It's generally not the amount of mitochondria that are the limiting factor in VO2 max. It's the ability of those capillaries and central circulatory system to get oxygenated blood to the mitochondria that limits us. Okay? That limits us. Most of you are not secretly like elite distance runners. You've just never run before in your life and you can double your VO2 max. Can't go from 35 miles per kg per minute to 70. Most of you can. There might be a couple of genetic outliers. I don't know. Okay? That's kind of what's happening. Okay. What happens to heart rate and stroke volume? Very interesting adaptation. People that are more highly trained have a lower heart rate at rest and a lower heart rate at any given work rate, absolute work rate, than a person or than they did when they were untrained. As a percentage of your VO2 max, it does not change. Okay, it doesn't change. Your heart rate at 60% of VO2 max is going to be the same, whether you're when you're really, really sedentary versus when you're really, really trained. That number will be different, but it's going to move around. Okay. At rest, people that are more highly trained have lower resting epinephrine and norepinephrine levels. You have higher parasympathetic activation, so you've got more acetylcholine. Okay. That is also then offset by increased stroke volume at rest. So these two things are inextricably linked. As you train, stroke volume goes up because your left ventricle gets bigger. For the most part, that drives most of it. The left ventricle gets bigger. As stroke volume increases, heart rate can go down, and we can maintain cardiac output. Okay. As heart rate begins to fall, there's an increase in filling time, there's more venous return, okay, which kind of further does this. And then as plasma volume goes up, blood volume goes up, that also leads to more venous return. So you're going to get this. So if you run today and we see an increase in plasma volume by tomorrow, we could probably, although it might be right at the edge of our measurement, see a measurable increase in stroke volume tomorrow. Okay. There have been studies where they've done 1 pound of exercise, and then they've been able to measure a very small but real increase in VO2 max 2 days later. So you go from like 35 mils per kg per minute to like 36. Okay. So all going to come down to those kinds of things. All right. Now, has anybody heard of something called hypertrophic cardiomyopathy? Anybody know what that is? Hypertrophic cardiomyopathy. Athletes in here, when you guys came to OU, did they do an echocardiogram on you? They make you all do one every year? You know what they did when you came? Yeah? They're measuring your heart size. Hypertrophic cardiomyopathy, an enlarged heart. Okay? An enlarged heart. Which in people of y'all's age is probably the single biggest predictor of sudden cardiac arrest. Okay? You guys, especially the ladies, have a heart attack like 1 in every 900,000 like exercise times. Okay, guys are like 1 in every 300,000. You get to be my age, it's 1 in every 8. Okay, every time you exercise, you take your life into your own hands. You really do, right? Much more likely to have sudden cardiac arrest when you make the heart work hard than while you're sitting there. It's still a tiny, like almost completely negligible increase, right? Especially in women, but it's real. Okay, hypertrophic cardiomyopathy means an enlarged heart. Some people have this genetically, and the thing that is a problem is the heart is enlarged and it has these very thick ventricular walls. Okay, that's why it's enlarged. Because you might think, great, I got a big heart. This would be good. I should have a high VO2 max, right? Well, one of the things that we see as people have high blood pressure and stuff is you get adaptations in the heart to where the left ventricular wall gets thicker, and that's very predictive of sudden cardiac arrest. That's what we see if you genetically have hypertrophic cardiomyopathy. Okay, so with people and cardiac hypertrophy, there's two kinds. We get the good kind that comes from aerobic exercise, that's sometimes called volume overload or eccentric cardiac hypertrophy. And then there's the bad kind, which is called pressure overload or concentric left ventricular hypertrophy. Okay? If you have high blood pressure, aortic pressure is high, the left ventricle must contract very forcefully to overcome that pressure. So that leads to hypertrophy in the cardiac muscle, just like doing lots of bicep curls or lots of bench press or lots of squats. The muscle grows like other muscles, like skeletal muscle, in response to resistance training. The heart gets bigger, but the ventricular space, the lumen, stays the same. The walls just get thicker, and for whatever reason, this is bad. Okay? When you do aerobic exercise, as you do lots of exercise, you force lots of venous return. Lots of Frank-Starling mechanism, it stretches the ventricle. Okay? As it stretches, that's an eccentric contraction in the left ventricle. It stretches it out, and that kind of overload leads to making the lumen larger and the walls thinner. So the heart enlarges, but it's mostly enlarging not by thickening, but by making the space and the size of the ventricle get bigger, so it can accommodate more blood. Okay? And that's a very positive adaptation. So what you will see, normal myocyte, concentric hypertrophy, the myocyte gets thicker, the wall gets thicker, it's stronger, but that's bad. That somehow leads to greater chances of impairments of autoconduction in the heart. Whereas when you overload it with venous return or with volume, you get this eccentric hypertrophy, and we kind of stretch out the cardiac cells. Why they behave this way, we don't really understand. Why skeletal muscle doesn't behave this way, we don't really understand, but that's what's going to happen. Okay? That's what's going to happen. That's why people that have chronic high blood pressure have sort of enlarged hearts, and it's bad. Whereas people that are sort of training a whole bunch have enlarged hearts, and it's good. Okay? It comes down to that. Okay. If stroke volume increases, cardiac output increases. Okay? Heart rate doesn't change, but if stroke volume goes up, cardiac output will go up. And you can relate a lot of this stuff back again to the Fick equation. If max stroke volume increases, max VO2 goes up. Max heart rate doesn't really change, so that has no effect. But then capillaries and red blood cells and mitochondria increase a VO2 difference. So that also then makes VO2 max go up. Okay? The training really has a big effect on those two parameters. Max stroke volume and max VO2 difference. And that drives most of that, say, 25% or so increase in VO2 max. VO2 max goes up really quickly, as I said a couple of minutes ago. You will see increases in your VO2 max within a week if you're training. Possibly within a couple of days, if we can get a good enough and precise enough measurement. Yet it takes mitochondria several weeks. So as I said, why would VO2 go up so fast? It's all about plasma volume. That part's all about plasma volume. Okay, is this the last slide? Nope. That's it. Okay. We got a couple of minutes. Any questions? You want to talk about altitude small mountain?
Is it final expensive or is it just this, stuff we're running right now?
The final is cumulative insofar as all of these things we've just been talking about with aerobic training are concepts that we've covered or related to things that we've covered all throughout the class. I'm not gonna pull out stuff from any previous tests. Okay? It's not really cumulative. Okay? Other questions? All right. Wednesday, we'll start doing adaptations to the heat, I guess. Our body, I'll kind of cover everything. All right, we'll see you guys then. Please bring your tests back. If you have questions, come see us.
Thank you.